Dear students, today we are going to discuss the power requirement in agitated vessel. Basically, the energy consumption in the mixing processes, it consumes a lot of energy, and as a result, one is cautious about the energy consumption, which is going to give the desired performance. So whenever the mixing operation takes place, what is its purpose? Based on that purpose, the whether it's a crystallization, whether it's a dissolution, blending, a chemical reaction, whatever the purpose may be, but the power requirement or the energy requirement, that should be the minimum one. That means with the minimum power consumption, we have to give the resultant output. And for that purpose, we can think of the different variables which can be associated with the power consumption. From that, the viscosity, density, the speed of rotation, the vessel diameter tank, these are the main prominent factors. Not only that, your gravitational force, that is also one of the important parameters in calculation of the power requirement. So density, viscosity, gravitational force, speed of rotation, and the vessel diameter. Not only these five parameters, but in addition to that, the process or the blending, whether it's a mixing operation, means purpose of blending, dissolution, dispersion, that can be there. Then how much amount of the liquid that is available in the tank, that is the liquid height, that is also one of the factors. But this power correlation, which is more commonly used for our calculation purpose, that is associated with the viscosity, density, gravitational force, speed of rotation, and the diameter of the vessel. And for that purpose, according to the pi theorem, the required dimensionless relationship that can be written as, it's a function of pi 1, pi 2, pi 3, which is equal to the 0. And we can write this pi 1, which is equal to function of pi 2 and pi 3, where the pi 1, pi 2, pi 3 are the dimensionless numbers. So the above parameters, that is related to the power, that I can write some constant c, mu raised to a, rho raised to b, g raised to c, n raised to e, and d raised to f. We have not taken raised to the power d because we are having the d diameter there itself in the equation. So writing its units of relevant quantities, that is most essential. Now when it's a function of a gravitational force, that is gravitational force is having the units of meters per second square, that is meters per second square raised to the c. Then density is having the units of kgs per meter cube. This density is having the units of kgs per meter cube. Then the vessel diameter, which is d, and having the units of meter. So these are the different units. In addition to that, the viscosity, that is Newton second per meter square. Newton second per meter square. And where the Newton is nothing but your mass into the acceleration. Where Newton, I can write mass, that is in terms of the kgs, and acceleration is meters per second square. So the units of viscosity, that becomes kg, meter, and this second upon the meter square. and second square. So by simplification, kg per meter second. So I have written kg per meter second. Similarly, the power, uh, which is having the units of watts. Watts is nothing but joules per second. So joules is again nothing but Newton meter is the joules. So watt is joules per second. Joules is Newton meter. Newton is kg meter per second square. So simplification, that is going to give you the kg meter square per second cube. So I can write this kg meter square per second cube, which is power raised to the 1. So I can write here power raised to the 1, that is there. Then the units of viscosity, kg per meter second. Then density, kgs per meter cube. G acceleration due to gravity is having the units of meters per second square raised to the power c. And n, the speed of rotation, the speed. So time is there. That is 1 upon second. That is the speed of rotation is having the units, which is raised to the power e. And d is your diameter, vessel diameter. So meter in terms of meters raised to the f. Now collecting all the equations related to the kg. So kg is there. Kg raised to the power 1 for this. For this I can write kg raised to the power 1. Here kg raised to the power a, and here kg raised to the power b. So 1, which is equal to the a plus b. So I can write here 1, which is equal to a plus b when I have collected all kgs. Next is seconds. I will collect the seconds. Here second raised to the power 3. That means it's the equation corresponding to the 3. Then second raised to the minus a. Second raised to the minus 2c. Second raised to the power e. So I will collect all the seconds, which is equal to a plus 2c plus e, which is equal to the 3. That is related to the seconds. And then finally I will collect for the meters. So meter square, which is meter raised to minus a, meter raised to minus 3b, meter raised to c, and meter raised to f. So minus 3b and minus 2c, that will be there. Minus 3b and meter raised to c. So that all the meters they have been collected. Now, so there are 5 unknowns, that is a, b, c, e, and f. So 5 unknowns and 3 equations are there. For that purpose, we'll write the equation in terms of the a and c and eliminate b, e, and f. So for the purpose of elimination of b, e, and f, I can write the first equation b, which is equal to 1 minus a. Then I can write e, which is equal to 3 minus a minus 2c. And similarly from the third equation f, I can write f, which is equal to 5 minus 2a minus c. So my purpose is that I want to eliminate b, e, and f. So equation, all these 3 equations, that is written in terms of a and c. So for simplification purpose, p, which is equal to c into mu raised to a, then the r raised to 1 minus a, that is nothing but the value of the b, which is your density term raised to the b. Then g raised to the power c, n raised to the power e, m raised to the power e, and f d raised to the power f. This is written here. So now the quantities with the identical letter exponents, they have been collected so that P upon uh, rho, this is R is nothing but your density rho. So P upon rho, then n cube, and then 5 d raised to the power 5. So all the constants with the 1, they have been collected, and they are uh, grouped in the left hand side, and all the a parameters raised to the power a, that is collected, which is nothing but 2c, sorry, the d square, the d raised to the minus 2a, then n raised to the minus a, and rho raised to the power minus a upon mu raised to the power a. So this is all minus a that has been collected. So that is going to give you d square n rho upon mu. Similarly, all c that is collected, which is going to give you the d raised to the power minus c, then n raised to the power minus 2c, and g raised to the power c. So there, all the c, they are collected in this group, that is d n square upon g raised to the power minus c. And now these groups, they have been defined in terms of the numbers, that is np is power number, which is nothing but p upon rho n cube into d raised to the power 5, which is equal to C into Reynolds number raised to the power minus A, which is equal to D square n rho upon mu, and Froude number raised to the power minus C, where Froude number is D n square upon G. So this is the relationship between the power number, Reynolds number, and the Froude number. And in terms of your mixing operation, this relationship is very much essential, and it is talked in terms of the different graphs. So it can be seen that the viscosity mu and the gravitational constant g are accounted only once, and each only in dimensionless number, where np versus nre is shown, that is the, now one by one number, this is the Reynolds number. In the design of agitated vessel, an important factor is the power requirement to drive the impeller. So empirical correlations have been developed to predict the power requirement, where all this d is the diameter of the impeller, then n is the speed of rotation, rho fluid density, and mu fluid viscosity. So this power consumption that is related to the fluid density rho, the fluid viscosity mu, rotational speed impeller, and so this power number that is defined as P upon rho n cube into dA raised to 5, and similarly np, which is equal to the in terms of the gc, if you will write, where it is in terms of the English units power, that is the feet, pound feet per second. Now here in this graph, it is plotted against the NP, that is the power number, versus the Reynolds number. So NP power number from 1 to 100, and from 1 to zero point 0.1, that is total scale of power number is 0.1 to 100. And the Reynolds number value are from 1 to 10 to the power 5. So for lower values of the Reynolds number, the power requirement is initially high. So this is the, if you will plot the different graphs for the different values, you will get the different lines corresponding to the power and the Reynolds number, where all these 1, 2, 3, 4 lines, they correspond to the different types of the impellers, and the number of impellers, it's a flat 6 blade turbine with the disc, flat 6 blade open turbine that is there, then 6 blade open turbine that is there, then it's a core 4 that will correspond to the propeller, then again fifth core that is corresponding to the propeller. So but the differences will be there. So all these are the lies corresponding to the different types of the impellers or corresponding to the different geometry or the number of blades that is going to vary. So this is the numerical which corresponds to the power requirement. We will see it. The flat blade turbine agitator with the disc having the six blades is installed in a tank similar. Uh, the tank diameter dt is 1.83 meter. The turbine diameter dA is 0.61 meter. Diameter of the tank diameter, which is equal to the liquid height, and the width of the blades is 0.122. It's a turbine impeller. The tank contains the four blades, each having a width J, which is equal to 0.15 meters, and the turbine is operated at 90 rpm, and the liquid in the tank has the velocity of 10 centipoise and a density of 929 kgs per meter cube. So calculate the required kilowatt of the mixture, that is the power requirement, and for the same conditions except for the solution having a viscosity of 10,000 1 lakh centipoise. Instead of 10 centipoise, I have changed the viscosity to the 1 lakh centipoise. So calculate the power requirement. So we will see the following data that is available, that is the diameter of the impeller, then width of the impeller, and then J that will be related to the baffles. Then diameter of the tank is 1.83 meter. Speed of rotation, that is 90 rpm, which is nothing but 1.5 revolutions per second. The viscosity, that is 10 centipoise, which is 1 into 10 to the power minus 3, which is equal to 0.01 kg meter second. That is nothing but Pascal second. And the density is 929 kgs per meter cube. So the power requirement, I can calculate it by using the formula, the above derived formula, that is dA square n rho upon mu. So this is substituting dA, that is diameter 0.61. N is the speed of rotation, that is 1.5 revolutions per second, and rho is density is 929 kgs per meter cube upon the viscosity, that is in terms of the kg meter second. So that is going to give me the 5.187 into 10 to the power minus 4. And if as it's a turbine impeller, so we can see the specifications related to the curve 1 of this. The curve 1 that is related to the turbine impeller with the specified number of the blades. I will select the NRE value of 0.18, and for this is NRE, which is equal to every. And then solving for the power requirement, the power that will be giving you NP rho n cube into d raised to the power 5. So this formula that will be required, that is the NP upon rho n cube dA raised to 5. So n cube rho into dA raised to the power 5, that will be there. So power that will be, so we are having the NRE values, and NP, that is nothing but the 5.187, 5.187 into the 10 to the power 5, that will corresponding here, and the first curve that will be there, this will correspond to the value of 5 here. So from this graph, this NP values, that will be the 5. Rho you are knowing as 929 kgs per meter cube. Speed of rotation is 1.5 into 10 to the power 3 into diameter of the uh, impeller, that is the 0.61. So power that comes as 1.324 kilowatts. When written in terms of the HP, that is 1.77 HP. So this is the simple calculation, and now you are going to change the viscosity. That is, viscosity is increased to 1 lakh centipoise. So into 1 lakh centipoise into 10 to the power minus 3, which will be is equal to 100 kg meter second, and dA square n into rho upon mu. So your Reynolds number, that will become 5.185 now. So this is the laminar flow region, very less. So NP, that will correspond to the 14. So power, that will be NP, which is nothing but the 14. So power requirement 3.71 kilowatt. So power requirement from 1.324 to, it is increased to 3.71. Means from 10 centipoise to 1 lakh centipoise, that is for an increase of 10,000 folds in the viscosity. The power requirement simply increases from 1.324 to 3.71. So that is the power consumption. This is our log of PO versus log of RE, that some authors, they have they write in terms of the log. So this graph is provided in terms of the log, and that is corresponding to the creep flow, transition flow, and the turbulent flow. So again, this is the graph related to the various types of the impellers and the geometries corresponding to that. So you will get the different geometries.